Okay, so last time we talked about rational functions, and we proved a fundamental property of rational functions, that is the following theorem for E over K with K algebraically closed, and two rational functions f and g from E to E. Sorry, I should have said rational maps. F plus G evaluated at P is f of P plus G of P for any P. And I mentioned that really the goal of the current few sessions is to understand the torsion points. So I think I gave this definition before, but let me repeat it. Suppose E over K is an elliptic curve. Where K is not necessarily algebraically closed. The n torsion points of E are E bracket n. This is the set of all points in E over the algebraic closure of K, such that NP is equal to the zero element in E. Now, I want you to notice that n torsion is not exactly the same as points of order n. I mean, if you remember, for any group, the order of an element is the minimal integer, the minimal positive integer, such that if you add the element to itself this number of times, you get the zero element. And here, n torsion points, I mean, points of order n are necessarily n torsion points, but not conversely. I mean, not necessarily conversely, because you could have some. So, Mark, if say K divides n, and P is a point of order K, then obviously P belongs to En. Okay, because I mean, K times P is already zero, and so when you and K divides N, so when you do it, I don't know, N number of times, you still get zero. Okay, so n torsion points is a bit more general than points of order n, but for n equals 2, it's the same, right? Because 2 is prime. So points of order 2 are precisely n torsion points. I mean, if you add, of course, the zero element, this depends on your convention, on whether you say the zero element has order infinity or something like that. But in any case, the zero element is an n torsion point by this definition. Moreover, En is a subgroup of Ek bar, because you take, I mean, if P and P prime are in En, and I add them together, and then I multiply by n, by the distributivity law, it's np plus np prime, which is 0 plus 0, which is 0. And similarly, if I do n times minus p, I also get, I get minus np, which is O. And so the n torsion points are a subgroup of Ek bar. And let's remark that I won't write, but I will say here, I mean, the reason that we want to take K bar, I mean, that we want n torsion points to be all the points in K bar that satisfy NP equal O, and not over K, is the good behavior that we saw for, for example, for points of order 2. I mean, we saw that points of order 2, which again, it's the same as n torsion points. In the case of 2, it's the same as n torsion points, or 2 torsion points. They have a uniform shape when I work over the algebraic closure. But I mean, so E2 is also a point of order 2 plus the point at infinity, and they always have the shape of Z mod 2 times Z mod 2. But if K is not algebraically closed, then it could be many things. I mean, it could be just O, or it could be some other kind of thing. So it's convenient for us to work over the algebraic closure where we expect that we have a uniform shape of the group. Any questions so far? Now, what we want is to understand the group, the subgroup. En. And can you say, do you have like a guess what should we expect En to be? It's not a difficult question. I mean, just extrapolate from the case of case that you know.
All points of order n and point at infinity.
No, that would not, because as I said, if n is not prime, I mean, if n has some divisor k, then points of order k would also be in En.
Then all points of order n and of order of all divisors of n and point at infinity.
Yes, that is true. But this is not a very useful description. I mean, this we don't need to prove. This is immediate, well, or almost immediate. But it's very hard for us to work with such a fact. I mean, and we have the case of n equals 2. In n equals 2, it was z mod 2 times z mod 2. So we can expect that En will be isomorphic to Zn times Zn. And this will be the case. Now, if you think about it, we have the structure theorem for abelian groups. So if we know simply the number of elements in En, E bracket n, then there are not so many options. I mean, the structure theorem for abelian groups would, first of all, so if we show that En has n square elements, we are almost done. And the reason is that since En cannot be isomorphic to Zn square, because I mean, Zn square has an element, many elements, but at least one of order n square, and En does not. So you see, I mean, if I know that En is of size n square, then I'm almost proving that En is Zn times Zn by the structure theorem of abelian groups, because I start ruling out other options by considering the order of elements. Okay, so this is the general aim of the next few sessions. And before I forget, I should say that on the 14th of July, I'm going to another conference in Japan. And that would be, and then I'll stay in Japan until the 4th of August. So the sessions between 28th and 4th of August will be cancelled. And I think that we could probably almost get this result in the next couple of sessions. What do you mean, Lisa?
Like to the 4th of August, like from next week? No, from the week after the next week, 14th.
From
And
14th of July until 4th of August. Every Friday that falls into this
I see.
period. Okay. So let NP be given, I mean, let's denote the functions that define multiplication by n. I mean, of course, if we want to understand a torsion points, then we want to understand multiplication by n. Multiplication by n is, I mean, I give you a point. Let's say p is some xy. And then you want to do np, that is nxy, in this, I mean, in the elliptic curve E, right? Then np is some expression in the first coordinate. It's some expression, polynomial expression in x and y, polynomial or rational function expression. So I call it gnxy. And in the second coordinates, it's also some function of x and y, right? So it's hnxy. So this is my notation, and we want to understand gn and hn. So I claim for K algebraically closed, Gn and Hn are rational functions. Yeah, rational functions. With poles precisely at En. And furthermore, En has finitely many points. Okay, so maybe just a quick question to you. I mean, we consider finite fields, or at least fields of positive characteristic. I mean, then typically we have the points in the elliptic curve are just a finite set. So why can't I say that En is, I mean, it's a subset of a finite set, so it must be finite. Why do I need this the last statement of the theorem? Lisa, what do you think?
Can you repeat like why do we need the last statement about finitely many poles in what context?
No, not poles, points. I mean, we work many times. We work with elliptic curves over FP, right?
Right.
And the number of points of an elliptic curve over FP or over FQ is finite. So why couldn't I say, okay, I mean, the number of points of the elliptic curve over FP or over FQ is anyway finite, and En is simply a subset, so it must be finite. Why do I need this orange part of the theorem? Why do I need to prove it?
Maybe because we want to be sure that we have finitely many poles.
Let's even disregard that part. I mean, why
Because we
is
work on the algebraic closure.
exactly the number of points in E over the algebraic closure is not finite. It's in fact it's never finite. This is something we talked about. I proved that. It's also in the notes. But I mean, the algebraic closure in itself is not a finite field. And when we talk about En, we talk about n torsion points over the algebraic closure. So if I don't know, I mean, if the number of points over the algebraic closure is infinite, then it could be that also the number of n torsion points, which is a subset of the number of points, of the collection of points of E over the algebraic closure, it could be that En itself is infinite. So this last part of the statement tells us that at least we can be sure that it's finite. Okay? Now, the theorem is in fact very easy. I mean, by induction on N, G1 xy is simply x, and H1 xy is simply y. So, right, because I mean, G1 H1 is multiply a point by 1. It's the same. It's like the identity function. So this is fine. So these are clearly rational. And okay, so this is the induction step. Now suppose that Gn and Hn, and of course E1, I mean E1 is finite. E1 is simply the point at infinity. There is only one point that if you multiply it by 1, you get O. So suppose that Gn, Hn are rational for all n smaller than q, and that En is finite. I guess this also for all n. So how can I say, I mean, how do I know that GQ and HQ are going to be rational? So for the inductive step,
Sorry, I missed the step. I was doing something else. Sorry, I was there as well. Can you repeat why again E1 equals 0 for the base in the case?
Well, what is E1? It's all the point in the algebraic closure that if all the points P in the algebraic closure, such that if you do 1 times P, you get O.
Yep.
Okay, and there is only one such point. So for the inductive step,
sorry, I don't see it. Like 1 times P for me, it's like 1 times G1 H1. So it's 1 times XY.
1 times P is equal to P.
Sure, but so it's not equal to 0 then.
Only if P is equal to 0.
Okay, but we don't say this. We don't say anywhere that P is equal to 0. So I don't see why you say N. No.
So En is the collection of all points in the algebraic closure, such that if I multiply them by n, I get 0.
Yes. So you have 1 time P, but you don't know if 1 time P equals 0.
I know that there is only one case in which 1 times P is equal to 0.
Okay, so it's when P equals 0. Okay, sounds good. Okay. Sorry, got it. Thank you.
No, it's okay. So for the inductive step, I write QP as a Q minus 1P.
I'm sorry, what is Q?
I do induction and I say that my induction hypothesis is that the statement is true for all n smaller than q, and then I will prove it for n equals q.
Okay, so it's just something larger than n.
Yeah, because I mean the statement itself involves n, so it's maybe nicer to pick a new integer.
Okay.
For the kind of the induction process. So okay, so I write QP as Q minus 1P plus P. And I mean, obviously Q minus 1P is G Q minus 1P, comma, H Q minus 1P. And by the inductive assumption, GQ minus 1 and HQ minus 1 are rational, right? And obviously, 1 times P, this is 1 times P. 1 times P is simply G1 of P, H1 of P, which is also rational. So what we have here, QP, so by the theorem of less time, I can write a Q minus 1P plus 1 times P as, let me put it like this, Q minus 1 bracket plus 1 bracket, and all these evaluated at P. This is like the sum of rational functions, or rational maps. Right? And this is, of course, QP. But I mean, but this is a rational map because it is given by a GQ minus 1, HQ minus 1, which we assume to be rational functions. And this is a rational map. So by the result of less time, we get that Q from E to E is a rational map. I.e., Q evaluated at P, which is just a fancy way to write a QP, and this is given by GQ of P, HQ of P, is rational, which implies, in particular, that GQ and HQ are rational functions. Okay? So this is the first part of the statement. I mean, the first part of the theorem is proved. It's, I mean, I just wrote it in a lengthy way. It's an immediate induction using the result from the less time. We are left to show that EQ is finite. This will follow if we knew that P into QP or rather a bracket Q from E to E is not the zero rational map, the zero rational map, I remind you, we denote as OM. Okay, this is like in the elliptic curve over the field of rational functions, this is the zero element. Yeah.
I'm not sure I understand this statement. I mean, I understand why if it is zero map, then the number of points won't be finite. I understand it, but I don't understand how we know that this is the only case when it's true.
Yeah. Okay. So if yeah, so as you said, if it is the zero map, then clearly EQ is so let me just expand here. If a Q is the zero map, then EQ is equal to E. I mean, to E of K bar. And so and then it's not it's never finite, right? E of Q bar is never finite. And if Q is different than the zero map, then there is let's say R in E such that Q let's put it like this. There is Q in E such that QQ is not the zero element. Yeah, you have a point. Something indeed is missing. Well, I mean, but remember that we have the inductive assumption. I mean, we know that a Q minus 1 brackets, it cannot be the zero map. So if a Q is not equal to the zero map, and EQ is nevertheless infinite, then we should have a problem. Then I mean, Q is a Q minus 1 plus 1. I mean, maybe the thing we want to use here is that a rational map that is not constant has to be surjective. So once I know that it is not a rational map 0, I actually know it's not constant. Because at the very least, a 0, I mean, this map maps 0 to 0, so it cannot be constant, hence it's surjective. If it's surjective, then I want to say that this will imply that E of yeah, something is missing here. How about we take a break? I think about it a bit. If I can fix it, I will, and if not, we move on to another part. So let's take a break of 10 minutes, and I'll try to fix this. Okay, so unfortunately, I was not able to fix this. But let me prove the statement modulo this fact. So okay, so let us show that a Q from E to E is not the zero map. If it was, then for all P in E, QP would be equal to 0. Which means that EQ is the entire group E. And now you have two cases. So, if Q is not prime, then I have some integer k that divides Q. Then clearly EK is a subgroup of EQ. And EK, by the inductive assumption, is finite. So let's say K is equal to, sorry, Q is equal to K times L. And if Q is in EQ, then I multiply Q by L, I get something in EK. Right? Because if I mean, because if I multiply LQ by K, then I get QQ, which is 0. Yes.
Sorry, there's another basic understanding I missed. I don't understand the the conclusion. If QP equals 0, then EQ equal EQ bar, EK bar.
I mean, if for all P, I mean, if the map a bracket Q is the zero map, then for all P, QP is 0, right?
Okay, so all the points would be Okay. So when you multiply QP, it gives 0. So
it's the quantification here. The quantification
yeah,
is
for all P's. Okay, so all P's are part of E of Q bar. So okay, got
yeah,
it.
all P in E K bar.
Yep, got it. Thank you.
Because the when I say Q from E to E, I really mean, and I think I already, I mean, this E is E of K bar. Okay.
Yep.
So, so if it was the zero map, then I would get that EQ is the whole group E, and therefore I could take any element Q in EQ and multiply it by L and get an element in EK. And we know by the inductive assumption that EK is finite. Since both EK and EL are finite by assumption, yes.
Yeah, me again. So here you're saying Q is part of EQ, and then you think so if we multiply Q by L, then it's part of EK. But you're doing L times Q, not L times K. Then
No,
so I'm a bit confused.
yeah, but Q is equal to K times L.
Sure, but you're doing Q times L, not K times L.
Yeah, but the elements of EK are the ones that if you multiply them by K, you get 0.
Sure.
So I took an element of EQ. It means that if I multiply it by Q, I get 0.
Yep.
And now I took this element. This element is not 0 in itself. We
Yeah,
only know that if you multiply it by Q, you get 0. So I multiply it by L. I get some other element. I don't know that it is 0.
Yes.
But I know that if I multiply this other element, LQ, I multiply it by K.
If you were to multiply it again, okay, and then you will get Q. Okay, got it. Thank you.
Okay.
Logic. Okay.
Okay. So we claim that if EL is finite, which is the case by our assumption, there are only finitely many points Q with LQ equals R for a fixed R. Why is this the case? I denote by phi R the map from E to E given by a phi r of Q is equal to LQ minus R. Phi R cannot be the zero map, since otherwise for all Q in E, LQ would be equal to the same thing, to R. And then if R is zero, it means that LQ is the zero map, which means sorry, L is the zero map, which means that EL is equal to EK bar. And that's a contradiction because EL is assumed to be finite. And if R is different than zero, then phi of R, phi R of O is by definition, it's it's minus R, and R is different than zero, so minus R is also different than zero. So phi R either, independently of the value of R, phi R cannot be the zero map. Okay? Hence, phi R has finitely many poles. Because we said it about rational functions, but this propagates into rational maps. I mean, rational function can only have finitely many points in which it gets infinity. And therefore, a rational map, because a rational map is two coordinates of rational functions, and the condition is that one is infinity, one gets infinity if and only if the other gets infinity. And there are only finitely many points for which each of them can get infinity. So altogether, the rational map can have finitely many poles. Okay, this is but and this, of course, the exception is the zero rational map. The zero rational map has infinitely many poles. But we know that phi R is not the zero map. So phi R has finitely many poles. And what are the poles of phi R? This is the set of elements Q in E K bar, such that LQ minus R is equal to O. Right? Or let me just write it like this. The set of point Q such that LQ is equal to R. And this is finite. This number of poles is just the number of elements in the set, and this is finite for any R. In particular, EQ I could write as the union of So EQ is contained EQ is contained in the union of all the poles of phi r for r belonging to EQ. Or sorry, for r belonging to EK. Right? Because we said that if a Q is in EQ, then LQ belongs to EK, i.e. LQ is equal to R for some R in EK, which means that Q is in the set of poles of phi R. Okay, this is maybe a bit tricky to follow, but it's not hard. So in our case, since it's I mean EK, since EK is finite, yeah, since EK is finite, EQ will be finite as well. Right? It's contained in a union of I mean a finite union of finite sets. This blue union. Is this point clear? So what I'm saying that if Q, this whole thing is, if Q is not if Q is not prime, and I pick some divisor of Q, then I get that EQ is contained in, I mean, in a union of finite sets, a finite union of finite sets, so it has to be finite. Is this point clear? Nicholas, what do you think?
Yep, there's some detail that mini detail later, but I understand the general yeah, makes sense. I will review.
Now, what do you? Where are you?
All good.
Yeah, I'm going through it. I mean, when you say it, it makes sort of sense, but it's always like when I try to explain it to myself, is when like I need to redo all the steps with more time. But I can
let me try to repeat the argument, and you know, if you don't get it now, we move on, and you can read more.
Cool.
I'm saying we are in the case. I mean, we are assuming that a Q is not the zero map. This is the orange assumption. Sorry, we don't assume. We want to show that a Q is not the zero map. So we assume that it was. If it was, I claim that if it was, well, EQ would be equal to to EK bar. Okay. Now there are basically two cases: either Q is prime or Q is not prime. If Q is prime, if Q is not prime, then I find some divisor of Q, K, and I observe that if I take a point in EQ and I multiply it by L, then I get immediately a point in EK. This you got?
Yes, this part, yes.
Okay, so now I claim that since EL is finite, there could be only finitely many points Q such that if LQ is equal to R. That is, I mean, and the reason is that, I mean, if I fix R, the points Q such that LQ is equal to R are the poles of this function. Right? I mean, it's the points Q such that LQ minus R is equal to 0.
Yeah.
Okay, so but this is a rational function. Rational function can only have finitely many poles. So the points Q such that if I multiply Q by L, I get any R that you want. For a fixed R, they are finite. But if I take R, I mean, as noted in this part, if I take R to be LQ, I mean, if I take Q in EQ, then LQ, which is R, is equal to, I mean, is an element of EK. So if I now say, I look at the poles of phi R. Imagine that R is a point in EK. I mean, this statement is true without the assumption, but we know that the number of points of phi R, the number of poles of phi R is finite because it's the number of poles of rational functions. But the number, I mean, the poles of phi R, if I run over all R in EK, these are exactly the points Q in EK bar such that LQ is equal to R. And in particular, this contains EQ. I mean, what I really say is that EQ is contained in the union of all poles of phi R. Because if I take a point Q, if I take a point Q here, then I take LQ, I denote it as R. Then a Q would be a pole of phi R. Right? Because LQ is equal to R. So LQ minus R will be 0. But phi R is exactly, phi R of Q is exactly LQ minus R. By definition.
Yep.
Okay? So you see, every point in EQ can be viewed as a pole of phi R for some R in EK. But by assumption, there are only finitely many points in EK. And for each of these points, the number of poles of phi R is finite. So EQ is contained in a union of finite union of finite sets. So it has to be finite. Which of course gives us a contradiction, because we assumed that that bracket Q was the zero map, meaning that EQ is equal to the whole of EK bar. Okay? I should say here, I should write round brackets. Okay, so yeah, go on.
One short question. So you said that the number of poles of phi R is finite because it's a rational function, right?
Yeah, it's a rational map, yes.
Rational map.
And you, okay, so we didn't exactly prove it. I mean, we proved something else. We proved that the number of poles of a rational function is finite, right?
Yes.
But what is a rational map? A rational map is just a pair of rational functions.
I see. Okay.
Each of these rational functions, and there is a condition. A rational map has a condition that implies that RP is infinity if and only if S of P is infinity. Okay? So, I mean, each of these functions, R and S, can only have finitely many poles anyway. So F can have at most finitely many poles. Okay?
So one thing that I'm not sure is, so you want to show that that EQ is finite, but then you show a lot of things, but it looks like just by showing that since EQ can be viewed as the union of poles of phi R.
Yes.
Since this is finite, then EQ is finite.
Yes.
So then EQ is finite without needing to go into the. I mean, I'm not sure what I'm missing, but
no, I'm saying like what is happening here is if we assume that the map Q is the zero map, then we get some contradictory issue, because if it's the zero map, then I have the orange equality, right? Then
yes.
EQ is equal to EK bar, which means EQ is not finite. But on the other hand, I get that EQ is contained in a union of finite sets, so it's finite.
Okay.
So this is a contradiction.
Okay, so all this procedure was to show that the assumption was a contradiction.
Yeah.
Okay, okay.
So
Thanks.
at the end of this, I should say a contradiction. Now, the other case, if Q is prime, then then E2 is obviously contained. It's in fact it's a subgroup. Well, it's contained. It's not. It's contained in EQ. Right, because if Q is prime and EQ is the whole thing, is E of K bar, then obviously E2 is contained in EQ, because EQ is equal to EK bar. And we know that E2 has 4 points. And it's a subgroup, right? I mean, E2 is a subgroup of EK. So it must be a subgroup of EQ. It means that 4 divides. I mean, it means that 2 divides Q, because the only way that E of K would divide E of would be a subgroup of E of L is if a K divides L, right? So this means that a Q is even. But Q is prime, and there is only one even prime, so Q is equal to 2, and that's a contradiction. Because E2 cannot be the whole thing. E2 it can only have 4 points. Okay, so hence, actually, now I think I can see how to fix the proof. So we proved that EQ is not the whole of E. Okay? But EQ is the set of poles of a rational function. I mean, GQ, HQ. Hence finite. And GQ HQ is not the zero rational map, hence EQ is finite. I understand that it was a messy proof because I had a mistake earlier, but do you want me to repeat the argument? This is this
Yes.
part. Lisa, where do you want to repeat?
I want to repeat this like connection, this
Say again, where?
like oh, never mind.
You get it? I mean, the gap that I thought I had, I mean, it's enough to show that EQ is not the whole group E of K bar, because we already know that GQ and HQ are or that multiplication by Q is a rational map, right?
Yes.
So and EQ, this is always true. EQ is always the poles of this rational map. And if this rational map is not the zero rational map, then EQ is finite. Okay?
Mhm.
But if we know that EQ is not the whole of EK bar, then we know that GQ HQ is not the zero map. It's an equivalent statement, right?
Yes.
Nevertheless, do you want me to repeat the proof from either from the beginning or from somewhere else?
No, I think it's good.
Now, what do you think? Where are you?
Yeah, no. So your last overview on the part of the proof where you show that it's final helped me to get on track. So I think I'm good now. So thank you.
Okay. Let me do one more corollary, which is maybe a nice application, but it's not something that we will use today. The rational function Gn minus x is not identically zero. Of course, for n bigger than 1. Because for n equal 1, it's exactly 0, right? Gn, I write Gn, but you should think of it, it's Gn of xy, right? It's like some rational function in two variables. And the proof is very easy using what we showed. If Gn minus x is 0 identically, then we would have NP is equal to either plus or minus p. I mean, it would mean that NP has the same x coordinate as p. So NP is either equal to p or to minus p. but NP equal to plus minus P is the same as saying that N plus minus 1 P is equal to 0. And this is for all P. Hence, either En minus 1 or En plus 1 would be infinite, would be, in fact, the whole group would be equal, would be E of K bar. And this cannot happen, right? We know that each of the ENs is finite. Okay. I think maybe it's a good place to stop here for today. We progressed a bit slower than I wanted, but it should be fine. I don't want to start a new thing. Do you have general questions on where we're going or anything else?
What is our plan for next 2 sessions that will be before the break?
So I want to show that the number of elements in En is n squared.
Right.
For that, we will need to examine carefully the functions Gn and Hn.
Okay.
Okay, so we will calculate, for example, the leading coefficient of Gn and Hn. And once we do that, we will go for calculating the divisor of Gm minus Gn. And after that, we will be in a position to show that En is of size n squared, and from there, a simple argument by using the structure theorem for finite abelian groups would show us that En is in fact isomorphic to En to Zn times Zn.
I see.
Okay. So if there are no other questions, then have a nice weekend.
Thank you. Bye.
Thank you.